This week I'm going to introduce a new method of calculating or deriving equations of motion. This method is called the Lagrangian method. But before I go into that, I think it's worth just quickly summarizing or reviewing how we've calculated equations of motion so far. For systems consisting of particles, we have the following two relationships that we use to get equations of motion. So we have the force linear momentum relationship, which says that the force applied to a particle is equal to the mass of the particle times the acceleration of that particle in frame A. That's the force linear momentum approach. And then we also have an equation called the torque angular momentum relationship, which says that the torque about some point Q is equal to the time derivative of the angular momentum of P about Q in the A frame, plus the velocity of Q in frame A crossed with the linear momentum of P in frame A. And again, that's the torque angular momentum approach. Now, for rigid bodies, well, first of all, we think of rigid bodies as a collection of particles. And what that means is that for every particle in the rigid body, we can calculate these equations, this force linear momentum and torque angular momentum equations, and essentially sum them all up. And for the force linear momentum relationship, what that simplifies to is that the force that's acting upon a body is equal to the mass of the body times the acceleration of the center of mass of that body in a fixed frame. And you can write a similar equation for torque. However, we can actually simplify those equations in the following cases. So for example, we can write the torque of a body about its center of mass, and that equals the moment of inertia, so I, about the body's center of mass, times the acceleration of the body in frame A, and that's the angular acceleration. We can also write the torque, make sure that's a T, right? So the torque of the rigid body about an instantaneous center of rotation, right? And so again, that ICR point is the point on the rigid body that does not move at a given instant. And we can write that as the mass moment of inertia of the body about its instantaneous center of rotation. Again, multiplied by the angular acceleration of the body, or you can think of that B as the frame that contains that rigid body with respect to A. And then lastly, we have the equation torque of a rigid body about some point Q, right? So just some point in the in your space or in your plane. You can write that as the moment of inertia of the body about its center of mass, again, times the acceleration, angular acceleration of the body with respect to frame A. But then you have to add in this additional term, which is plus R, so the position vector that takes you from Q to the center of mass of that rigid body, crossed with the mass of that body times the linear acceleration of that, the center of mass in frame A. Okay? And then we also have a special case, and this was for when you had a single particle or rigid body, and you had a conservative system, meaning only conservative forces do work, right? So again, conservative forces are forces like gravitation or spring forces. And in that case, we could use this following equation, which says that kinetic energy plus potential energy is equal to a constant. And so this was our conservation of energy method. By understanding how to use all of these equations, you now have the knowledge and the tools to generate equations of motion for any system that consists of particles and or rigid bodies that moves in a plane. And that's quite powerful and a very, very useful skill to have, not just in mechanical engineering, but for engineering in general. And so this week, I'm going to introduce just yet another tool in your toolbox that will allow you to calculate equations of motion. You will always arrive at the same answer, assuming you do it correctly, but you just simply have a different approach, a different tool that you can use to derive these equations of motion.